Welcome to the third part of lecture number 3. This one is specifically about the layouts. So in the last lecture we discussed sort of a very quick overview of what the fabrication process is and how the chips are manufactured. In this one we will go into the layout of the gates and what kind of useful information as electronic engineers we can extract from layouts. So this is the outline of this presentation. We will first discuss the standard cells layout. As I told you, standard cell are sort of a library of gates. So standard cells are like the library, okay, used by fabs. So this is something they can do easily. So they put all these different kinds of gates in their standard cell library. Then we will discuss the stick diagrams. So basically a stick diagram is sort of a simplified model of layout. Okay, then we will discuss this Eulers method or Eulers path, which basically is a certain kind of optimization or let's say you can say a certain kind of optimization for layout slash stick diagram. So a stick diagram is just a simplified form of layout. Then we have certain kind of design rules which makes sort of the layout more reproducible or easy to automate. So layout rules basically pertain to the transistor channel length. You will see that all the rules are related to transistor channel length, which we denote as lambda. Okay, and lambda is basically L by 2. So L is the channel length and lambda is L by 2. So it's basically all the dimensional considerations. We will deal with that in design rules. So let's go into the details. So a layout is a complex process, and consequently it can be very time consuming if you do not use the library of gates. So if you use a library of gates, one of the advantage as a designer for you is that you can accelerate the process of your IC manufacturing. Okay, so standard cell methodology, it basically says that we should use VDD and ground, so they should have standard height. Okay, all the adjacent gates should satisfy some design rules, which we will cover in the coming slides. And then we say that NMOS should be at the bottom and PMOS should be at the top. Okay, so your NMOS are at the bottom near to your ground, and your PMOS are at the top near to your VCC. Then all the gates must include well and subtract contacts. So this is I told you that when we are developing everything inside a single subtract, for example, this was the P subtract, this is from the last lecture. So here we had the NMOS, and here we had the N well, and inside the N well we had this PMOS. Okay, so what this says that we should have the contacts of the body terminal here and also here. Okay, so this is the contact of the body terminal or the fourth terminal. So normally we draw 3 terminals for transistor, but I told you that there is a fourth terminal. Okay, that's sometimes called body terminal. So it is for that. So every gate should also include these terminals. So these are some of the let's say more high level design methodology using standard cells. This is the layout of an inverter. So let us go into some details of how this is an inverter. So as you remember that an inverter has PMOS and it has NMOS. Okay, both of them are connected in this kind of fashion. So we have the VDD, we have the ground here. Okay, and basically this is your source, this is your drain, source, this is gate, this is gate. Okay, so let's try to see what are the how the different things map. So this is the, if I consider the PMOS, this is the N well. Okay, this is your well, this is the VDD. So this one is your source, this one is the drain, this vertical line is your polysilicon. Okay, so whenever there is a polysilicon, on one side you will have a source, on the other side you will have a drain. Then we have these black things which are basically what? They are contacts. So they are metal contacts. So for example, this metal contact means that the drain is shorted with this one. Okay, with this vertical strip, and basically this vertical strip, this one is your output, this is your output Y. So this is the strip for your output Y, and this polysilicon, this one, okay, this strip is your input. Why this is input? Because this is the gate of PMOS, this is this strip is the gate of NMOS. This gate and this gate, they are connected by the polysilicon. So this is this line. Okay, so this is this is this line. Okay, this is the line at the input. So this is our A, and our output is this one. Okay, this one is our output, which shorts the drain of PMOS with the drain of NMOS. And you can see that the source of NMOS is in contact with the ground. Okay, so this is the overall structure. This is in this one the wells are not connected, but if you see, here is the difference for the version B. We have here the subtrate tap and here we have the well tap. So I told you about the fourth terminal. So these are like the fourth terminal, which is connected for PMOS to VCC, and for NMOS it is connected to the ground. So why we have this connection? Because this is what the standard cell methodology tells us to do. Okay, now let's go into this one. I hope you will not get afraid of this one. This is basically a 3-input NAND gate. So just to remind you what a 3-input NAND gate looks like, is something like this. We have 3 transistors, A, B, let me make it a little bit more, separated, split out from each other. So this is our transistor B, and this is our transistor C, and we have here our ground. So we have 3 transistors in series. We have our Y, and then this is our VDD, and here we have, let me correct this one. We have this PMOS, this is the first PMOS, this is the second PMOS, this is the third PMOS, this is A, B, C, okay, and they are all shorted with our VCC, and then we have all these shorted together, and this is our point of output. Okay, so this is our CMOS static circuit. Let's see how this is translated into the layout. Maybe we should start with this part, okay, which is our pull down network. It is here. So our pull down network is entirely located here. Okay, so you can wonder how these transistors are connected and what is basically a transistor look like in a layout. So basically a transistor is something like this. You have this subtract, and whenever on top of this subtract you have the polysilicon strip, this one. Whenever you have this kind of this plus sign, so on one side a source and on the other side a drain will be formed, and this strip of polysilicon is your gate. So this is the same for NMOS and for CMOS. They both look like this in the layout view. So you see, just keeping in mind that concept, we see that here is our transistor A, okay. So let me see. So okay, let me make this according to the layout. So this is A, B, C, okay. So you see now the source of A is connected to ground, and here is the drain. So you see this is the ground, and this is our transistor A. Why this is our transistor A? Because here we have the polysilicon going from top to bottom. So on one side of this polysilicon, there is the source of a transistor, and on the other side there is the drain of a transistor. Okay, transistor number A. Okay, so you see that the source is shorted with the ground through this contact. And what is this? This is the contact for subtract. This is for subtract T. Okay, this is the fourth terminal which is connected to the ground. And then we consider the B transistor. So if we consider the B transistor, you see that here is the drain, source, okay, source, drain, okay, or even you can see that this one is the source, drain, okay, source, drain. Okay, so this is transistor B, this is transistor B, okay, and this is transistor C, and they are in series, okay, because they are connected. The drain and source of A and B are connected, the drain and source of B and C are connected. Okay, so they are in series. It will be clarified when we discuss the upper one, how parallel connections look like. But before going into that, let's talk about this point. So you see here the drain of transistor C, okay, so the drain of transistor C is connected with this one, okay, it's connected with this contact, and this whole contact, if you see, this is our source, this is our source, this is our source, this is drain, drain, drain. So all the drains are connected to Y, and you see this is the drain, this is the drain, okay, so it is connected, it is connected, it is connected, all the drains are connected. Okay, so this is the drain of C, the drain of A, they are shorted. You can ask what happened to the drain of B. So the drain of B is here, it is, the source is here, the drain is here. Okay, for C the drain is here, the source is here. You may ask how I select on which side is source and on which side is drain. Basically, if you look at the transistor, the drain and source are symmetrical. You can call one source and the other drain, doesn't matter. It only depends on your supply. Okay, so you connect the supply to the source, and the drain is used for interconnection, it is used for drawing up the current. So it doesn't matter, you can swap the source and drain. Okay, okay, I think now and okay, so let's see, this one is again transistor A, and it is connected to the VDD. This is again the N well tap, so this is the fourth terminal, and then the VCC is connected here. So you see the source of B and the source of C, they are both here. Okay, so this is important to understand. They are both connected to this point, and they are both on this side. So this is how a NAND gate is formed. Okay, now let me tell you how these dimensions come out. This is another important thing from this layout. Okay, so before explaining, I think I should remove all the this annotation, or better, I should move to the next slide and explain the area estimation. So let's move to this slide, and what I want to show you, that how we can estimate area from this kind of layout. So let's see. As I told you before, that lambda is basically your channel length divided by 2, and this is sort of the fundamental you can say quantity in which we will a fundamental feature in which through which we will measure every other dimension. So as you know that area is just length multiplied by width, so we want to estimate what is L in terms of lambda, so n lambda, and what is W in terms of this n lambda. We need to find m, for example, the values of n and m, the multiplicative factor for lambda. So let's start with the vertical one. Okay, so you have to remember this thing. What we want to count the metal layers. So this is our metal layer 1. Okay, but this is in parallel with this one. Okay, so there is no need to consider this one again, because the height of this and this are equal, so we will only consider this height. Then we come and we say that there is another metal layer from here to here. This is our second metal layer, so we are not considering this one again because both have the same height. Then we say that we have this one is our third metal layer, and then we have from here to here we have our fourth metal layer. Okay, and you see there is some space here which says 4 lambda. So basically you calculate all the metal layers, which comes out to be 4, and you add 1, which is for this kind of adjustment of our VCC line, and you multiply this with 8 lambda. Why we multiply with our 8 lambda? Because this is, in the coming slide we will see why 8 lambda, but for now just say we use to multiply all the tracks or this number with 8 lambda, so it comes out to be 40 lambda. So this is this 40 lambda. Now let's move to the horizontal direction, and for the horizontal direction you can calculate the width either from the end diffusion, okay, which is this whole line. You can do it from here, or you can do it from the P diffusion layer, which is this line. Okay, so which one we have to choose? we have to choose the one where there are maximum contacts between polysilicon layers. Okay, so we see here is a polysilicon A. We have this contact, this contact, this contact, and this contact. So we choose the P diffusion region. Now we have to count the spacing. So one is this, we have the second, and we have the third. So we have 3 and 1. We add a 1 to this. Okay, so this is for safety margin, and this is multiplied by 8 lambda, again 8 lambda. So 4 into 8 lambda is 32 lambda, which is this one. So what is the area estimate? The area estimate of this 3-input NAND gate is this one is 40 lambda into 32 lambda. So this is the area estimate of a 3-input NAND gate from the layout. Now maybe for some people the layout is difficult to understand or comprehend, so we go to a more let's say simplified model of the layout, which is called stick diagram. Okay, so what is a stick diagram? It is just a simplified model of layout, and it is not to the scale, and it's better to draw with color pencils, but you can use just a black or blue, anything, but it's better to draw in multiple colors. So for example, here we have the legend of colors for different layers. So metal layer 1, as I told you that inside the IC you have like a building of layers. So we say metal layer 1 is this one, so this may be metal layer 3. Okay, a modern integrated circuit can have 17 or 18 or 20 layers. Okay, so they are like a stacking of layers. So the polysilicon or poly is in red, the N diffusion is green, the P diffusion is yellow, and the contact is represented with a cross. So let me ask you, what is this one? Okay, so this is basically N diffusion, okay, with one layer connected to with one terminal connected to the ground. So basically this is the polysilicon, okay, so which makes this a NMOS. So this one is a NMOS. Why NMOS? I told you, whenever you have this plus, and this one is the poly, and this one is your diffused region, you have a transistor. So if this diffused region is N diffused region, then it is a NMOS, and if this is a P diffused region, it is a PMOS. So here you see this is a PMOS, okay, and the poly lines are connected and labeled A, and the So this is our source connected to VCC, our drain connected to the drain of NMOS. Okay, so this is our output Y. So what is this? This is basically an inverter, a CMOS inverter. Okay, let's come to this one. What is this? So you see the green diffusion was for NMOS. So we have the NMOSes. How many NMOSes? 3. 1, 2, 3. The source of one NMOS is connected to ground. The drain of this is connected to the drain of this. Okay, and here we have 3 PMOS, and they are in parallel because this is the source of A, this is the drain of A. Sorry. This is the source of A, the drain of A. This is the drain of C, the source of C. Okay, and this is the source of B, and this is the drain of B. So these drains are connected. The drain of A and B are connected to the drain of C, and they are connected to the drain of C in the NMOS. So they are in parallel. You see the source, so both the sources are connected to the VDD line. So this is the stick diagram for the 3-input NAND gate that we discussed in the previous slide. You see, it is more, let's say, easy to try. It is much easy much easy to draw compared to the layout. Okay, so this is called the stick diagram. Okay, now let's discuss something that is called Eulers Path. What is a Eulers Path? It is basically an optimization for stick diagrams, or for that matter layouts, because a stick diagram is a simplified model of a layout. And why we need this Euler path? Because the Euler path can give us a layout which has minimum, let's say, contacts, okay, which translates to, let's say, minimum delay. Minimum delay means your circuit is fast. It also translates to minimum power consumption. So basically it optimizes the layout to give you enhanced electrical properties. So what is the Euler path or Euler graph? Basically you treat the source and drain as nodes and the gate as edges. So basically the approach is a graph theory approach. You translate all the sources and drains to nodes and all the edges to all the gates to edges. For example, let's say this is our transistor and we say this is source, this is drain, this is gate. So the Euler representation or Euler graph will be like this. The source and drain will be denoted as nodes and this gate will be denoted as this H. Okay, and then visit all the nodes and edges such that the nodes can be repeated but edges cannot be repeated. Okay, I will go through an example to make you understand what this means. And the last one is path patterns for pull up and pull down must be the same. Okay, so let's go to this example. So the example is like this. We have this a plus b c whole bar, and we want to implement this circuit. So first go to the static CMOS circuit, or let's say just CMOS circuit. Why I have it in static here? Because later in the course we will study dynamic CMOS circuit, but for the moment let's say we want the CMOS circuit. Okay, so we have B and C, and the B and C are ANDed, so they are in series. Okay, and then we have A, which is in parallel, and then we have this point which is connected to ground. Okay, and let me change, let's say, the color to maybe this one. Okay, and then we have the other one, the pull up, in which B and C will be in parallel. So I have this PMOS and I have this PMOS. This is my B, this is my C. They are in parallel, and we have the last PMOS in series with B and C, and from here we take our output, let's say Y. Okay, so let's go through an exercise to build the stick diagram of this one. Okay. So one option is this one, that we put this is B, this is C. I told you this kind of plus sign, this kind of plus sign is for transistor, it can denote any transistor. So I put these three pluses. Okay, and then here I have the ground line. So you see the source of C is connected to the ground. Okay, so this is a contact, this is the source okay, sorry, so this is the ground, and let's say this is the source. So the source is connected, this is the source of C, this is the drain of C. Okay, the source of C is now connected to the ground. This is the drain, this is the source. Okay, so you see the drain of C is connected to the source of so this is the drain of C is connected to the source of B. So this is the source of B. Okay, and then the source of A is connected to the ground. Okay, and the drain of A is connected to the drain of B. Okay, this is the drain of B and this is the drain of A. So you see, this is the drain of A, this is the drain of B. So this is the pull down network, and then we go to the VDD line, and you see this is the source of A and this is the drain of A. So I put another plus. This is the polysilicon, this is our A transistor. You may say this is the source, so the source of A is connected to VDD, and this is our drain. Okay, this is our drain, and then this is our source, this is our drain, this is our source, and this is our drain. So we have two more transistors, B, this transistor B, and this is C. Yes, this is C. So now the source of B is connected to the drain of, so this is our source, this is our source. Okay, so these sources are connected and then they are connected here. Okay, so this is our connection, and this is the drain, this is the drain. So both the drains are connected. Okay, and then both are connected here, and this is our output. Where is our input? Our inputs are all these lines, all the polysilicon lines. So for example, C is connected to this, B is connected to this, A is connected to this poly. Okay, so basically this is B, this is C, and this is A. All the poly lines are connection to the input. This is B, this is C, and this is A. Okay, so these are interconnections for the input. Whenever there is a poly line, that means input. So this is one stick diagram, but this stick diagram is non-optimized. This is non-optimized. optimized. Why? Because you see there are so many broken diffusions. Okay, unlike the layout which we have seen in the previous slide in this lecture, the diffusion regions were not broken, but this one is broken. Okay, because this is a non-optimized stick diagram. So how we can create an optimized stick diagram? It can be created with the help of Euler's method. So what the Euler method says is like this, that we need to convert our. So let's build the Euler graph, and for that let me change this to this color. We need to take the nodes. So we have this one, this, let's say, our first node. This is, let's say, our X node, and this whole is, let's say, our Y node. So let me draw the Euler graph, which says that we put VDD, then we put X, then we put Y. Okay, so this is, I'm doing this for the PMOS, and between VDD and X I have A. This is transistor A. So you see the source of transistor A is connected, the source is connected with VDD, and the drain is at node X. Okay, so these are the two nodes, but instead of labeling it as source and drain, we are labeling it as VDD and X. We can use any names for these nodes until we can understand it. Between point X and point Y, there are two transistors. One is our B, and the other is our transistor C. So this is our PMOS, or let me say this is our pull up network, and we can do the same. So this is our node Y, okay, and this is our node, for example, Z. This is our node ground. Okay, so let me pull down network. So we have this Y node, then we have the Z node, and then we have the ground node. Okay, so from Y to Z I have transistor B. From Z to ground I have transistor C. Okay, from ground to Y I have transistor A. Okay, so this is the Euler graph for the pull down network. Okay, so what is the importance of pull down network? The importance of pull down network is this, that we need to find an order of input variables, and this order will determine how we lay out our variables so that we have minimum number of contact points, minimum number of broken lines, or diffusions. So all we want to use a single diffusion for n type and a single diffusion layer for p type. Okay, so let me change the color again. Let me use for example this one now. So now I start with oh, this is invisible, so let me change again and maybe use black one. Okay, so I can start from any node, so I can go from this to this, then I can go from this to this, so I can go from VDD to D, X, then from X to Y, and then I can go to this. So this gave me an ordering of A, B, C. Let me see if the same ordering can be found in pull down network. So we start with A. Okay, can we go from A to B? Yes, there is a path. Okay, so we go from A to B. Can we go from B to C? Yes, there is a path, and I come here. So you see the path completes. The path completes here and the path completes here. Okay, so it means that if I want to go from A to B and from B to C, it is possible in the pull down network, and it is also possible in the pull up network. Okay, so this is an acceptable solution. There can be another solution. For example, let's say that I want a different path. Okay, so let's say I start from C. Okay, last time I started from A, so now I start from C. So from C I can go to if I go from C, let's say, to A. Okay, so I covered this edge once. Now I have, when I go here, I have to come back again. Okay, so this is not a correct path. Remember, one of the rule was that you can visit a node multiple times, but you cannot visit an edge multiple times. So I cannot go from C to A and then come back, because in that case the A will be visited twice. Okay, but let's say, let me redraw this in the red again. This was our transistor A. So let me switch back to this one. Let's say I go from C to B. Okay, and then go to A. Okay, so this is okay. Can I do the same? So this is our solution, C. This solution is C, then B, then A. in this solution I visit all the nodes and no edge is repeated. Let me see if I can do the same in pull down network. So I start with C, and from C I go to B, and from B I go to A. So I visited all the nodes and no edge is repeated. So this is also an okay solution. Both these solutions are okay. Remember the solution that we tried, C, A, B, that was not okay because the edge A was repeated. Okay, so let's accept the solution ABC. Let's use this one. So this is our order of variables. Now using this order of variables, let's draw the step diagram, the optimized step diagram. Okay, so the optimized step diagram can be made like this, that we start with these. This is our ground line and this is our VCC line. Okay, then after that, let me use a different color. This is our end diffusion. Okay, and let me use another color. Note that I am just using random colors. It is not according to the legend that I showed you before. So this is the P diffusion region. Then let's make the polylines. So we have 3 polylines. 1, because we have 3 inputs, 2, 3. So this is our poly. Now here comes the order. So the first one should be A. Okay, the second one should be B, and the third one should be C. Here again, A, B, and C. Okay, now you see here that the source of C and the source of A are connected to ground. So this is the source of, let me draw the connection, sorry, in different color. So let's say this was our end diffusion, and let's say I mark the interconnection in black. So this is our black. So source of A connects to the ground. Similarly, the source of C, which is this one, okay, this connects to the ground. So this is the source of C. Source of A and C are connected to the ground. Then the drain of drain of C and source of B are connected. The drain of B and the drain of so let me correct this. The drain of B, you see, the drain of B and the drain of A are connected. So we have these two connected here on this line. Okay, we have both the drains connected. Okay, this is source and this is drain for C, and the drain of these two, they are connected to our output. So we have a connection here. The drain of A and the drain of B are connected to our output. Now let's go to the, so this completes our pull down network. Let's go to our pull up network. You see, in our pull up network, the source of A is connected to the VDD. So this is VDD, here is our connection, this is the source of A. Then the drain of A is connected to the, so this is the drain of A, it is connected to the source of B and to the source of C. So we take this line, okay, and we connect it here. So this is our connection. So the source of C and the source of B are connected to the drain of A. You see here, the source of A, B and the source of C are connected to the drain of A. And lastly, the drain of B and drain of C, which is this point, they both are connected to our output. Okay, so this is the whole layout. The whole layout is now generated. You see, this is optimized. Why this is optimized? Because all the NMOS or the pull down network is on a single N diffusion layer. Okay, similarly all the PMOS are on a single P diffusion. If you compare it to the non-optimized one on the left, there are many broken lines. Here there is not a single broken line. So this is optimized implementation, and this implementation will have a minimum delay. It will have minimum power consumption because the interconnection points are less compared to the interconnection points in the left. So this is the advantage of Eulers path. Let's move to